positive. So I'd like to welcome Geetha Manjunath. She's the CEO of Niramai, and she's going to deliver the closing keynote for us. And she's going to talk to us about how her team brought an AI solution for breast health to the doorstep of women, and how they're now actually taking it to other places where it's most needed as well. So go ahead, Geetha. All yours.
You're on mute. Please unmute yourself.
Okay. Is this fine? Can you see me and can you hear me?
Yes.
Okay.
Yes, all good.
And can you see the slides more importantly? Okay. Good evening, girls and women, ladies. Great to see, very, very enthusiastic AI crowd here and, wonderful panel discussion as well. Very, very apt. How do we make AI really work in real life? And I guess the organizers have done a great job. So what I'm going to share here is more like a story of how it's working, but, happy to sort of take questions as to, of course, this also came from research to proof of concept, and now, happy to share that, it's commercial and being used by many, many women, to save them from deaths due to breast cancer. Yes, breast cancer is one of the largest cancer killer in women. 500,000 women die every year because of this disease, and it's unfortunate that it is so, because it's very unfortunate because it's one of the very few cancers which can be completely cured if detected early. And so what we need to do is to enable early detection, right? Unfortunately, in India, every alternate lady detected with breast cancer is dying. Yeah, 50 to 60% mortality, where you could actually have 90 to 95%. There's several reasons for this, and I just briefly touch upon this. Some of you would have heard me in other forums, but just to sort of give additional context, there's several gaps in the current screening method. And in a real forum, I would say, how many of you know, given that most of you are women here, how many of you know what is the standard test for breast cancer? That would say that, immediately, right? How many of you have gone through a mammography, for example? And I can't see all, but I can guarantee you it will be less than 10% of you here. So that's the main problem, right? Because one is awareness, what do I do? Like, what needs to be done to detect early abnormalities? It doesn't have to be cancer, no, everyone doesn't get cancer, very, very few people. However, everyone needs to check for it because we don't know who those people are, right? So that's the main thing, right? So of course there is some self-breast examination, but mammography is pretty much the de facto standard for detecting breast cancer. And what you're seeing on the right side are mammography images, which is basically X-rays of the breast of two women. One is the first one is a, let's say, 60-year-old. Second one, let's say, is a 40-year-old, right? Of course, it's anonymized and we don't know who it is, but this is the typical way it looks, right? And what you would observe is there's a lot of whiteness here, and there's less white and only white dot here. And the white dot is the one which mammography is trying to catch as something abnormal. It may not be cancer again. It could be a small lump called microcalcification or a fibroadenoma, very small, variation that requires attention, though, right? So when you're trying to do this, for a lady above 60 years, it's pretty okay for a radiologist to take a look at this, as a, just human being looking at the image, right? And then find that there is this white spot. What happens is that for women under 45 years of age, and many even above 45, they have a characteristic called dense breast, which is basically more fibrograndular tissue, which makes this whole thing look white. Okay, so because there are lots of glands, all of them are dense, so it looks white. And now the question is, where is the problem? Is there a problem at all? And where is the problem? It's actually humanly very difficult. Even machine learning is actually very difficult because, we are looking for dense tissue. Here you could write a machine learning model today. So one basic thing is that, the current methodologies do not, work on women under 45 years of age and dense breast. Another usual thing is the affordability angle. A test of 3,500 to 4,000 rupees is not affordable for every lady, definitely not in India, because we are saying, even when you're well, everything is okay, you need to do this test once a year, sorry. So that is, for that, it is not affordable. If there's a problem doing it, it's not very expensive. But this is not a diagnostic test. This is a screening test. Once somebody is found to be slightly abnormal in this, a follow-up test is recommended, and then biopsy and so on. That is what is more diagnostic in nature. Because of that, very few hospitals actually have a mammography machine. In fact, the mammography machine itself costs about 1.2 crore rupees. And how many hospitals would be able to put this in? It works only for breast, it works only for women above 45, maybe half of women above 45, many women don't go in. So with all this, if you look at what's called return on investment for this whole big machine, they don't have it. They have it in few hospitals and few diagnostic centers, which again affects the accessibility. All in all, it just makes it very hard for people to go for simple screening for breast cancer. And to top it all, there's also radiation exposure, so mammography should not be used every year. So what happens, if it's only done, let's say if I do the test today, I can only do it in 2022. What happens between the 24 months, right? Any of the abnormalities won't wait, for the next mammogram. So all of these issues have resulted in almost 90% of the ladies on earth, are not able to detect their early stage abnormalities through technology enabled solution. All they do is hand examination, right? So if by chance somebody figures out that there is a lump during taking bath or whatever, and they realize it's growing and they cannot hide anymore, only then they go to hospital. That's not good, right? That's the reason why we find 86,000 women who died last year in India alone, right? All of them, or at least 70,000 of them, could have just lived. All you needed was an early detection test, right? So no, this is just I'll go into how this works and so on and so forth. And so that's where NIRAMAI, I didn't spend too much time introducing myself, but yeah, so I'm the CEO and founder of NIRAMAI. I used to be actually at Xerox Research, and some of the speakers earlier, I've had the pleasure to work with them as well during the day, whoever came and spoke. And so I was heading the data analytics research at Xerox. And that's when, one of my cousin sister got detected with breast cancer, and I just said, okay, why not work on this, and started doing the research and so on. So in NIRAMAI, from NIRAMAI rather, what we have developed is a solution which can detect before the hand can feel. That's important, because I didn't tell you, when you want to feel it with hand, it's 2.5 centimeters, which is stage 3, stage 4. And that's when the difficulty comes in, right? You want to be able to detect if there's an abnormality before you even feel with your hand. So that's what is very most critical piece for early detection, let's say. That is, asymptomatic screening is important. Symptomatic is also important, but asymptomatic is super good, because if a person undergoes a quick treatment, she can live a very, very happy life for 35, 40, 50, 60, whatever years. It doesn't, recur, or rather it recurs less, and then it's really a nice. Otherwise, if it's late detection, even the health of the person, gets deteriorated after that. It becomes very difficult. So that's one thing. In fact, our results, clinical trial results, show that we are able to detect malignancy and also benign condition at 4 mm and 5 mm, size, lesion size, whereas hand detects 25 mm, right? All of you are math kind of people, so you know what that means. It's like 5 times smaller doesn't mean like 5 months before. It's like multiple years before, and so it's like very, very important for the lady to have a good treatment efficacy. The second important part is it's completely privacy aware, right? All said and done, we feel very awkward to go and sort of disrobe in front of a technician and do this test every year, and oh my God, need to go, and there's compression from mammography and all of those. It's like really not a very super good experience. And to top it all, if there's a male radiologist and all, we hear from our male, radiologist friends and say, okay, I've shifted out of breast cancer specialization because women hesitate to many times too much. It's not always true. I mean, it's not necessary, but that's also a major issue. So what we did was we made this completely privacy aware, and I haven't even given you what the magic is, but basically the person enters into a booth and she comes out. Nobody is inside. There's a sensor. Actually, we use a thermal sensor. Some of you may know already that it just measures the temperature variations on the chest. What you see here is a thermal image. Of course, COVID has made thermal screening very popular, right? Thermal cameras are placed in many places like airports and all. The same thermal camera with a specific resolution requirement we have. So that's placed, and we just measure the temperature variations in chest. Nobody is inside the booth, not even a technician. It's almost like a changing room in Fab India or whatever, the malls you may go into. So you just go in, close the door, go in. Of course, it has to be disrobed. The person sits in front of the sensor, and she comes out after 10 to 15 minutes, and her report will be ready, and that will be powered by machine learning. That is, the report is generated completely using machine learning and of course general AI techniques. And now, because we're using thermal sensing, there is no radiation. We just measure. It's a thermometer. It's a remote thermometer. So we just measure the temperature. So that's sort of very makes it more no radiation. That means you can actually do this just every 6 months, every 3 months, whenever there is an abnormality, especially with family cancer history and all that. Every 6 months, just doing this quick check is helpful. And then it because it's very privacy aware and there's no radiation, you can do it anywhere else also. It doesn't have to be in a hospital with thick walled radiation protection rooms or anything. Conferences, IoT Next conference, and even RSNA, it's a biggest radiology conference in Chicago. So all of these places we have done it, and we are now also doing a home screening, right? Go home and just 15 minutes in your own bedroom or bathroom, you could do this test. The technician is outside, nobody is seeing. So that's important. And it does work for women under 45 years of age, and several, also it works on men because there's no flesh to be put between the two plates and so on. And we made it pretty affordable compared to mammography, and we'll discuss all of those, if required. And most importantly, it's a very portable. It's almost like this, my water bottle. It's as big as that. I don't have a camera with me. It's actually smaller than this. So I can just put it in my water bottle, in my backpack my bag essentially, and then take it and then do it. So that's why home screening also is feasible. So all this is possible because of machine learning. And let's see what happens and how it's happening. Radhika, how much time really I will have now from now onwards?
About 10 minutes.
Okay, cool. So this is sort of the crux of the matter. So maybe we'll skip the video then. So we just have to sort of give it a nice name. So we gave the name of the technology as thermalytics, but honestly, it's a bunch of machine learning algorithms beautifully stitched together. So the end-to-end solution will work, right? So this is basically a library of machine learning algorithms. So what happens is when you take an image from a thermal sensor, we have this kind of a thermal image that comes in, where every point here, every pixel here represents the temperature at that particular. So you're looking at 400,000 temperature points, and every pixel here is the temperature at that point. So I mean, this is basically a heat map, right, of seeing the whole data that you're seeing at one shot. And that's what we analyze along with several other demography information to actually give a score which says what's the likelihood that there is an abnormality, what is the area where there is likely abnormality. Like you see, the marking, the annotation is also automated. And this is never done before. People have tried using machine learning on thermal imaging, in pockets, but not with good enough results so that we can actually go on the ground and actually give this as a solution to the ladies and actually find people who require help. So with all this, we have 9 granted US patents and several more under pending. So basically, there are 2 modes we do. One is real-time reporting for villages and all, where you cannot take a radiologist with you to do the signatures. So there we give a red, yellow, green. The lady doesn't see, the organizer sees, and then takes required action. For red, the family is contacted, and we ensure that a follow-up test is done. In a hospital like, let's say, HCG and Narayana Hrudayalaya, where we already have it, and also Cloud9 and so on. So we actually generate a full-fledged report, and also images where this annotation is there. There are 5 views that we take. The ladies need to rotate on stool to take the 5 views. And then we mark the area of potential abnormality here, and we send this out to the radiologist for certification. So it's like an end-to-end solution. This is how this small it looks. This is there in multiple hospitals, and you can also do it in different camps and so on. I wanted to play a video, but please look out for patient experience NIRAMAI, you'll find it. So what's under hood, right? Many of you are technologists and you'll be thinking, how is it going to work? And I just want to, give credits to Shiva and Himanshu, who has been with me in sort of in working through this for quite a bit. And what you're seeing here is a real image of a screening that's happening in a corporate camp, right? This is how the screen is put, and the technician is outside and sort of monitoring the booth. So what's happening, right? So first and foremost, the core innovation is that not thermal sensing. Thermal sensing is around and so on. And also the fact that thermal sensing can be used for detecting abnormality is also something that a few doctors have tried before, right? From a medical science perspective, because when there is a tumor, there is higher metabolism and higher heat generated because there is more activity, right? And that's what this is roughly trying to capture. But then there are several reasons why there is going to be an increase in temperature. And you can see that a person who has a cyst is here, a person with hormonal activities is in the bottom two, and this is a normal, and this is possibly a malignant condition. So if you just use bare eyes or do some simple analysis, you would basically find asymmetry here, and all those things. So you may call out. But unless you're able to differentiate between a pure real malignancy and this, there will be a lot of false positives. Almost 60% of the ladies who do this have some redness out there. That doesn't mean it's cancerous, right? Because people ask me, because it's red, is it cancerous? You don't have to worry, because there's several other reasons. And that's what we are trying to differentiate as one of the main machine learning algorithms. And initially, I think there was a comment made, right? If you assume that there's like millions of data points and I will go in and do it, no, sorry, because when we came out, of course, we did some initial analysis in my previous organization, but there we had like 78 patients, literally, yeah, 78 patients. And then we came out, we had to do some more, and then we had to build the model with just about 100 to maybe maximum 300 patients, and that's when we were able to go out, right, to actually have the good amount of accuracy. So deep learning is ruled out at that stage, right? So initially we started off with very semantically oriented. We started reading literature to figure out what type of features do doctors look at in other modalities, not thermal, because we don't have too many doctors doing it, and so on. So that's that. Then and also we also came up with some newer ideas as to what type of patterns could be. So it was really data engineering, image processing, computer vision, kind of a combination. And then we had a hand woven feature list, I would say, and then started off with that. And then as we started getting, we also still got a very good result in this. And then we started using this alongside existing modalities in different cancer hospitals. And then it also added to our data set. And now we have 150,000 plus images. And, obviously, now we are moving into deep nets and so on. So we are seeing good performance improvements as well in that space, especially to handle images which are not taken properly. We want like simple technicians to be our screening people rather than doctors doing it. And because of that, there are lots of errors in imaging, and there we find deep learning helping us a lot. So just to see it as a pipeline, what happens is several machine learning algorithms in this whole end-to-end solution. I only talked about the final classification very, very briefly and a cursory way. And you would see that first we will do an image quality check, as I mentioned, people have to take 5 images per person, have they take it properly, and so on and so forth. And then segmentation, identifying the area where the breast itself is in this whole image. That's not simple. So again, there's segmentation. And then we need to figure out different structures which aid to the readability, right, semantic interpretability of the report. So those things we do, and so on, right? So just to give you a flavor of it, I have like 2 problems here, double clicking and to show you some fun elements in this. So the first very simple problem in the first box that you saw is about people taking 5 images, and then these are like really girls who will do it, and they had to be called as left lateral, left oblique, left underscore LAT. They used by being very, very especially right RIGHT, they would write RIHGT and all that, right? So all these type of things were happening, and left and right they used to get confused because there was a mirror kind of an effect you get, right? So all of these. So first thing was basically view labeling, looking at these images and saying which one is which image, right? That's a frontal left lateral left 90, that is left 45 left 90, and right lateral, right oblique, we say. So those 5 views had to be learned. And initially, in the beginning, we were actually using image processing, curvature detection, and then trying to sort of, give a view label. And that was giving about 75, because when you say 45 degrees, they don't actually sit 45, they will be like 30, 25. So all of these errors, because of that, 75. But then when we actually when we had about 10,000 images, we started using deep learning, 10,000 to 550,000. So that's, we made it as a 5-class prediction, 5-class classification prediction, and then use a ResNet 50 architecture with some specialized loss functions. And so we were actually able to get up to 97%, accuracy, like a dice, accuracy in this case. The next piece is about, once you have an image, how do you identify the actual area that needs to be analyzed? Where is the breast type thing, right? And here, obviously, it's an annotation problem, and like a UNet or a VNet works pretty well. And we, of course, we did have a imaging computer vision or image processing based approach. I'm just showing the DeepNet part here. So we used CNN, and so the interesting part is the left and the right could be flipped to actually some data augmentation also. So we kind of used both together, just a feel for how these two things are. Anyway, so there are also, I also already talked about the N classification. So yeah, so this gives you the difference between a heuristic based approach like a contour detection, and then trying to figure out where is the breast, versus the yellow and the green is something that you may want to do. So that's obvious what's the difference. And what's also nice is that deep learning is able to detect different postures. So when you say you want to sit like this, they end up slouching, they do a lot of things, they make a lot of errors like this, most of the stomach is visible and all that. Still, it's able to work so beautifully. We actually do manual segmentation, even after this, to make sure that there's no error, because that's a very important input we need for that. And we right now are put 92.92 dice similarity with this. So showing that really it works right on the ground. And after that is where the actual analysis starts. So moving forward, so the overall solution itself has been tested as in used by more than 32,000 women so far, not all patients, sorry. And what's so amazing is that ASCO Breakthrough is one of the biggest conferences, breakthrough ideas. This is the American Society of Clinical Oncology. Last year it was held in Thailand. We were judged in the top 50 abstracts for this as well. And what's very interesting is that touch wood, we have not so far missed any asymptomatic cancer. When it becomes symptomatic, there are several symptoms. It's a diagnostic case where usually the doctors also struggle. Even there, we have got up to 92% accuracy. And just to give you an idea, this 100% for mammography is 66.7%. So that's the sort of the huge difference that we are able to find several women who didn't know that it existed even after having a mammography. And it's not just we said positive and hence, so it's actually proven by biopsy. All of these are biopsy proven cases that we are talking about, and several other nice things. And happy to sort of chat with each of you who are interested. So just as a detour, right, that ends my breast cancer, deep dive in some sense. But I just wanted to give a 2-slide flavor in the current context of COVID. All of us know, all of us are working from home, and we're doing this conference all because of this beautiful and unprecedented challenge that the world has faced, which is the COVID screening. So what we said was, how can we use AI and the computer vision techniques that we are aware of to address this? And so we have solved 2 problems, in the team. And trust me, and I'm putting this to sort of just hopefully incentivize and motivate some of you there to actually pick up some of these problems right from the world and start solving it, right? So and we were able to put this together in 1 week or 2 weeks time, the first version. Of course, after it got very, very interesting and people started using it, we have put in more effort on that. But basically, one is called NIRAMAI fever test. Essentially, people, security actually text the thermal value of the person who is walking in to every building, every hospital, and so on. And that's has become a mandatory thing now. Now, obviously, there are several disadvantages of manual thing. I won't go into more, but most importantly, this is not safe for the security guard because he is not wearing a PPE. It's also not safe for this lady because this one is touching multiple people. Actually, many times it's not remote, right? It's supposed to be. So we said, okay, how can we use thermal imaging and AI to provide a completely automated community screening solution. So as and when people walk by, and this is a real screenshot of what's happening there, and we just put a tube light behind, because tube light is 100 degrees Celsius. So we do face detection in thermal view, because thermal actually doesn't show you who this is. In fact, I mean, I can tell you what the names of these people, because they're I know them, but the privacy angle, again, we talked a lot about the data privacy. So we do this in face detection in the thermal modality, and then also figure out where is the eye, where is the forehead, where is, and also nose, and also the eyeballs. The temperature of the eyeballs is important. So all of that, and then we give the temperature on the forehead, and this happens automatically. People just keep walking by, and obviously if that something is abnormal, we give an alarm, and we give a log, and all of this good stuff that we could do with around this technology is there. And this is available again commercially, and now many in 3 cities they have already started using it, and this is really useful. They have found it really useful, especially in hospitals as well. So this is computer vision in action, right? And like I said, we built it in 1 week, the first version, and then we have evolved the face recognition on, we put in later, and so on. So this is one favor, I would say. Another one from a COVID perspective, again, this was probably a little more than a week, but this was completely out of public data, and each one of you can do it. And that's why I want to bring this in. And here we've also collaborated with ISC, Professor Chiranjeev Bhattacharya and his team. So where initially we were working on this, and Chiru got interested, and so we said, okay, let's collaborate, and we do have a collaboration now. So all we have done is like looked at all the chest x-rays available. There's also ChestNet, and there's COVID patients data also available. So we downloaded that and wrote a COVID, likely COVID patient detection, right, using chest x-rays, because as you know, right, it is a respiratory infection at the end of the day, and it shows up in it. So why is it useful? So in the villages, right, and talukas, the x-ray is easier than doing an RT-PCR test of your swab, throat swab test. Because if you take a throat swab test and send it to a district hospital, it takes 1 day to go there, 2 days to test, and 1 day to come back, or maybe phone pay, yes or no. But the patient is now, she has lost 3 days, right? But his chest x-ray is available. So we have launched a WhatsApp-based analysis where the doctor, the village doctor, basically takes x-rays are available everywhere. So he takes an x-ray of the patient who is suspicious, has symptoms, and so on, and he just takes a pic from his mobile phone and posts it onto this WhatsApp group. Immediately, our solution generates this report and gives the probability of COVID. And if the probability of COVID is higher than the label is positive, he is immediately sent to the district hospital, right? And then the swab test is available, and he's taken. And trust me, we released it on 5th of July, and by 10th of July, we had 257 doctors using it, and more than 100 COVID patients detected. This was one of the fastest go to market, and we've been talking about how to take things to market, and this is the fastest I've ever seen in my life so far. And I worked on like 100+ projects now, right? So that's sort of the thing this brings in, and I really urge each one of you to look around and see, like, what problem can I solve? What problem can I solve with what I know already, which is basically all of you know machine learning. All of you are here to learn machine learning. So if you start solving real problems, there's so much joy in seeing actual things work and really make a difference in somebody's life. Thanks a lot for listening. And there are several other yeah, this one. So all of these, are particularly the breast cancer one, has resulted in NIRAMAI being the only Indian startup, only Indian company in the top 100 AI startups in the world by CB Insights. And so I'm like super proud about this particular slide. And if you've heard me before, I always put this up and say, Mera baat. Okay, good. Hope you found something useful here, and happy to answer any questions.
Yeah, thank you so much, Geetha. It's all about saving lives when it's when we talk with you. So thank you for that. So if there are questions, guys, please put them into the Google form, and we'll get them to the speakers.
Okay. There's no live question. Okay.
Yeah, we're at the end of the event. So in closing, we've talked about this conference for a long time, and finally we've done it online, but we've seen that it's contributed 6 excellent sessions, and hosted almost 150+ attendees, and there is so much dialogue in general on so many aspects of AI and ML in multiple contexts. and there are more opportunities for discussing challenges and opportunities for AI and ML, in the Indian context also. So Intuit will continue to foster such an exchange of ideas across, such a diverse set of folks and applications.